That's why I'm so excited about robotics because it's like we are inventing ourselves, right? It is in many ways a quest to understand us and our intelligence. And it's so hard to put down onto paper how we detect like a cup or how we are doing these things or how we are planning tasks. Like, you know, how software engineers say the best way to learn something is to build it. And I think robotics is basically our quest to understand ourselves and build more of ourselves.
Hello, and welcome to the Cognitive Revolution, where we interview visionary researchers, entrepreneurs, and builders working on the frontier of artificial intelligence. Each week, we'll explore their revolutionary ideas, and together we'll build a picture of how AI technology will transform work, life, and society in the coming years. I'm Nathan Labenz, joined by my co-host, Eric Torenberg.
Omniki uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in Omniki so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.
Keerthana Gopalakrishnan, mother of robots, is a robotics and machine learning engineer conducting advanced robotics research at Google AI, where she's been an author on several of the most influential papers of the last year, including SayCan, which demonstrated that language models can effectively act as the executive planning function, or brain, of a robotic system, capable of understanding and carrying out, quote, long horizon, abstract, natural language instructions, unquote, by assessing situations, decomposing problems into parts, and issuing logical next step commands for their robot bodies to execute. And also Robotics Transformer, or RT1, which demonstrated that the same large-scale pre-training paradigm, which has recently delivered so many breakthroughs in so many domains, can also work for robotics. RT1 ultimately delivered a 97% success rate on some 700 different tasks. It's a truism in Silicon Valley startup culture that it's easier to manipulate and control bits than it is to control atoms. And some have argued that the impact of AI will be limited to digital domains as a result. To me, Keerthana's work strongly suggests that this outlook is wrong. Google's most recent release, Palm-E, as well as OpenAI's GPT-4, show that computer vision is still improving rapidly. And at this point, the combination of visual and language understanding seem quite clearly rich enough to support general-purpose robots, suggesting that relatively few major conceptual problems, including more general robotic control, which Keerthana suggests we will likely achieve by teaching robots to learn from watching humans, still remain to be solved. Barring an unexpected slowdown, my takeaway from this conversation is that we should expect many form factors of robots that can see, communicate with us in natural language, and solve basic problems on their own, all in just the next couple of years. At that point, the race to engineer and scale the production of all sorts of robots will be on, and shortly after, we'll begin to encounter them in factories, offices, businesses, and even homes. I enjoyed this conversation with Keerthana tremendously. She is technically deep, and we get into the weeds. But she's also extremely thoughtful about how her work will affect the future, and I very much enjoyed her thoughts on the big picture as well. I hope you enjoy this conversation with Keerthana Gopalakrishnan. Keerthana Gopalakrishnan, welcome to the Cognitive Revolution.
Thank you.
Really excited to have this conversation. A lot to cover. You have one of the best Twitter bios that I've seen, mother of robots. And as soon as I saw that, I was like, all right, we've got to get Keerthana on the show and talk to her about everything that she's doing. You've had quite a tour de force over the last year and change as well, in terms of having been an author on some of the biggest papers in robotics. And obviously, you've worked with an outstanding team at Google to create that work. But really looking forward to getting into some of the weeds on that. You recently gave a lecture for the ML Collective, which I have watched and definitely recommend. And one of the things that you said in that lecture that really caught my ear was that we're somewhere between GPT-2 and GPT-3 in the world of robotics. So I want to just start by asking, what does GPT-4 look like in robotics? Or zooming out even more broadly, how do you think we will integrate robots into our lives as they get smarter and more capable over the course of, say, the rest of the 2020s?
I'm very excited because we are seeing the type of scale, learning at scale in robotics. So, which is similar to like GPT-3 for language. So, like, we are seeing emergent capabilities in reasoning and also in low level control. And the way that I see robots coming into our lives is definitely, I think at Google, at robotics at Google, we have cracked this recipe of like transformers for control, language for interface, and then foundation models for like reasoning. um, I feel like this recipe is fairly generalizable and extensible and has the potential to scale with data and with compute. So the way that I see robots coming into our lives is where humans interact with robots in natural language, and the robots can do a lot of instructions in the real world, and they can think and plan in visual language space.
So, without being, falsely precise in terms of like a, specific date for a prediction, does it seem realistic to you that we are headed for a time within the decade where we might have, for example, domestic service robots that can like do the dishes for me after dinner, or pick up the toys after my kids and put them away when the kids don't do it? What is this going to like actually look like in homes or in places of business for people?
Oh, absolutely, I do. In fact, the tasks that we train our robots that we publish on are in office environments, and like picking things and cleaning and everything. In robotics, there is the problem of like a lot of demos that you see are like fairly staged. If you look at like robotics technology, there was like very traditional control like PID control and like search algorithms and stuff, and then there was early deep learning like end-to-end deep learning, but which was mostly like con nets and everything, and now there is transformers in robotics. And so we are seeing like a curve, and we are seeing that transformers are actually pretty good at doing a lot of tasks with one model, which is quite similar to how you are, right? Like you can cook, you can clean, you can like plan tasks, you can talk to your kids, like language generation. So I feel like to build a robot that's like very useful, that goes into different people's houses, it's going to be very generalizable, and it's going to be one model that's good at a lot of different things. And we are kind of seeing those trends already. The question is like, so we know it works in like multiple Google kitchens. RT1 can do a lot of tasks, but Google kitchens are still very similar and still a very small subset of the total number of kitchens that people can see in the world. So like, how do you scale fast enough that you can bring the generality and complexity of the real world into the models, and where like you bring that to my house and then it doesn't suddenly break down?
Yeah, it's a unbelievable convergence across kind of all the things. We've talked to guests who are in computer vision and who are, just touching all these different modalities, and the same story is kind of underlying the progress in all of them. So no surprise to learn on some level that that is also happening in robotics. I think one of the things that you talked about in your lecture, and you kind of alluded to there, is just scale. Is starting to happen in robotics as it has happened in other modalities, but the data doesn't naturally exist, right? That's like a huge difference between, for language we have web scale data. For we just did an episode on generation of human like voices, and obviously there's a ton of voices out there. I cloned my own voice. It took only 10 minutes of audio because there was so much pre-training. But obviously that doesn't exist in robots or for robots, because we don't have all the robots. They're not out there doing tasks in today's world and collecting data. So I was really interested. I kind of dug in a little bit to the RT1 paper and tried to get a sense for the work that you guys have done to assemble the data set, at least like beginning to approach the scale that is needed to power this. And I want to get into that a little bit deeper, because I think that's something that people probably have no real intuition for. And you have lived it, and put hours into helping to assemble that data set. So maybe we could just like run down some stats and then get like very kind of practical in terms of what the data is and how you're going about collecting it. So you've got, this is from the RT1 paper, 700 tasks, 130,000 episodes, which I take to be an attempt to complete a task. You can, definitely correct or refine my understanding. Multiple different robot form factors, and a project that took a year and a half to complete. I guess for starters, can you like just describe the robots? There are a few videos out there that people can watch to also kind of go see them. What are these robots? What do they look like? How big are they? What do they like to be around? Tell us about the robots.
Firstly, a lot of questions here. So let me go part by part. The robots are really cute that we currently use. So they are mobile manipulators. They can drive, and they have an arm with a gripper at the end. You can also like fit different tools, like they can do wiping and other things. Um, and they also have like self-charging and other capabilities on top of that. So they are really, and I think like they're a pretty good and fairly stable stack, and we have a fleet of them, and we have been collecting data on them. And the way the 130K episodes for use for RT1 are supervised learned. So they are collected by a human teleoperating these robots to do different tasks, and over the so they will attempt all of these tasks, and then we train on that using supervised learning. So now that brings you a question about like data and language and vision and stuff. So in language and vision, as you said, there's a lot of free data available on the internet that you can just take and then use, and then you're good to go. But in robotics, okay, there's reasoning and planning for which there is a lot of data, because it's similar to both humans and robots. But for actions specifically, there is not that much data. So that is one bottleneck in robotics, and it is also like a very engineering bottleneck. Like it, very few people can collect and accumulate data sets of that scale, which means that very few people, like robots are expensive, and you need like a lot of engineering effort to like orchestrate this large data farming operation. So that already means that very few people can do robotics, and also which is why like I feel like we at Google, who have the opportunity to do it, are really we really have a unique position in scaling and making a dent in our attempt towards solving robotics. So I'm very excited about that. But also, if you look at language and vision, the acceleration in deep learning was achieved by weakly supervised learning. Collecting data using robots can only scale linearly, and only scale, especially with like human demonstrations, it can only scale with O of humans. But we want to scale faster than that. And so one way would be to get transfer from human manipulation data. For example, imagine how you would learn to surf or cook something. You would take a YouTube video and then you would watch it. And there are a lot of YouTube videos of humans doing a lot of things. Imagine that like one day you want to train, like, let's say an NBA level basketball player, but who's a robot. You would not do like teleoperate robots to do NBA level basketball or do self play. Maybe you'll do a little bit of reinforcement learning and specific fine tuning on top, but you would make it watch all of the NBA videos that humans have been playing all these years, and then you would show, and you would try to get the robot like scaled up to that point, and then collect a bunch of data to like exactly fit to the robot's embodiment. So transferring from human manipulation to robot manipulation is a problem that we haven't yet solved yet, which I think is going to be very important in really solving robotics. So while humans cannot scale that fast, robots can actually scale. We can build like 50,000 robots. It's just a question of money. And then if robots can do autonomous collect, then that's going to scale faster than with supervised learning. So how can robots do autonomous collect? So one is like using these foundation models to like collect data zero shot or with a little bit of fine tuning, like something like code as policies.
So let's build up those layers in a little bit more detail, starting with the supervised learning, like the 130,000 episodes. So if I understand that correctly, you've got essentially a kitchen, which is the lab on the Google campus, and you've got robots that as of the time that you're collecting these episodes, are not AI powered. They are instead remote control powered. So somebody sitting there with like a PlayStation controller going around and, picking up napkins and whatnot with the robot. Is that actually like a reasonable picture of what's happening, like a PlayStation controller type of interface?
Yeah, we have like Oculus controllers for these robots, and then we have like multiple mock kitchens, which are like they're called robot classrooms. Like the robot goes to a classroom and learns some things, and then once they can reasonably do things in the classroom, then they are brought to like our actual kitchens to do like stuff.
I just did the most like naive math. I just divided 130,000 episodes by the number of workdays in the year and a half that the project took. And I got 367 episodes collected per day. So if I'm envisioning this right, it's like you must have, I don't know, 20 people who like have been operating the robots and like doing the actual VR to robot housework and collecting all the data. And then I understand also that like the robot sensors, sort of robot proprioception, I guess, if you will, is also being just recorded at like each timestamp along the way. And once all that is done, now you have kind of the, reasonably big data set for supervised learning. So then your inputs would be the task or the command or the instruction plus the imagery that was seen at that given time plus like state of the robot at that given time, and then the model is predicting next action. How many like data points does that translate into? Because it's each episode presumably has, I know you're running like multiple inferences per second, so do you have a sense for what that 130,000 episodes would translate into in terms of like example predictions, so to speak?
Yeah, so it depends on the median task length, right? So, and it also depends on what tasks. For example, picking is something that is fairly fast, and I think it's about like 30 steps. So you have 30 actions to pick an object, and like something like opening doors is longer episodes. So because you have to like approach the door, grab the handle, then open the door. So let's say if we put a median around like 40 or 50, let's say 50. 50 steps per episode, then each step has around 8 plus few, like let's say 11 tokens. So that's how many, and then you multiply that with the number of episodes. So it's like still way smaller compared to like language and image data sets. So we need to scale both by autonomous collection as well as by like transferring.
Okay, cool. So we've got the foundation of all this manually collected data, and now tell us kind of the outlook for the self collection. So I'm kind of, I do this with language models where I'll try to get it to do a task. It sometimes does it, it sometimes can't, and then I basically siphon off the data that is good, that shows successes, and like feed that back into my fine tuning, and I get better that way. Probably a lot of our listeners are familiar with that general kind of cycle. How does that, is that basically what you're doing also in robotics, or what is the kind of, robotics twist on that?
So right now our system has like a high level and low level control. The high level control runs at like lower frequency compared to the low level control is like much faster. And the high level control, that paper is called SEICAN, where a language model is deciding how to plan, like what task to do in sequence. So imagine something like, bring me a coffee. So it'll be like, go to the kitchen, find a coffee cup, pick up a coffee cup, place it on the counter, and then go to the coffee machine, press a button. So like there's a series of steps of steps in natural language to do to achieve like a small task that you tell the robot to do, which is like go get me like a Coke can from the fridge or something. So there is a language model which is like planning how to do the series of tasks, and then there is the robotics transformer which is executing each of the smaller tasks.
I'd love to just hear more examples of what the tasks are, and maybe your overall kind of impression of where the robots are today in terms of like, are they practically helpful? Like if you had one at home, would it be worth it, to have one at home at this point? Or is it still more trouble than it's worth? Like how close are we to actually having something that would be useful in the wild?
So it's not in the wild yet, and that's one thing that we are working towards. But the thing is, scaling from 5 to 500 is quite hard. But scaling from 500 to 5,000 tasks is easier, and 5,000 to 50,000 is going to be also easier. Like each of them are like a different class of problems. Right towards the end, you come to like more scaling and distribution and inference at scale problems, but initially you have algorithmic problems, and I feel like we sort of more or less have the algorithmic problems down. So if the tasks in RT1 are mostly like pick object, place knock pick, open cabinets, take things out of drawers and put them on counter, also open fridges and close. Technically things that you can do in a kitchen. And we also tried in like various Google kitchens. So it's like, yeah, if you take it to a new Google kitchen and make it run there, I think it should work. But if you bring it to your house, I doubt it will work because all the images kind of look like it's very out of distribution. I don't think it would generalize that much, but Google kitchens are still like somewhat similar. Things are at similar heights and stuff, so it should sort of work. So then that is the question of like generalization, right? And also like how many objects or how many scenarios can we generalize to? So the initial RT1, we wanted to focus on skills. So we were like, we will do a lot of skills, but a few objects. So we only had like 17 objects. Now 17 objects are like too small, right? You have millions of objects in the real world. And in order to be realistic, you need to be manipulating millions of objects. So which was our recent paper on like open vocabulary object manipulation. So the idea there is that, so imagine you can do 17 objects, and then you collect a little bit of data on about 100 objects. So generalizing from 17 objects to any objects is quite hard, but generalizing from 100 something objects to any objects is slightly an easier problem. So this was like, yeah, so what we did was use a visual language model that can do a lot of zero shot detection, right? Like right now, language models can differentiate between your faces. Language models can say, hey, this is like a bottle, or this is a phone, just from a zero shot image. So can we use that information to go manipulate that object? And it sort of works reasonably well.
So what are like the high end tasks? You kind of gave verbs, of knock, lift, open, grasp, etc. And then you also kind of talked about the longer time horizon planning, which I imagine is still like pretty short. Like it sounds like the things are, tasks that would be like 30-second tasks for a human. But like how far is that currently going? Could the robot, for example, like actually make and deliver a coffee with like actual hot coffee in it?
So we don't let them handle hot objects yet, and they're also not good at operating machines yet. But that's something like, because we just didn't collect data on it, but that's something fairly doable and that you can learn. They probably shouldn't be handling like hot coffee. I doubt that. That's probably like, I don't know. Like imagine you're carrying a hot coffee and then there's like a kid nearby, like, or like something happens and then you splash it. That's not good. Or you just pour it over yourself and then you break your electronics. So if you think about tasks in a kitchen, let's say when you're cooking and stuff, you only actually do a finite number of skills, but you are able to combine them in various fashions. So if you do let's say you have 100 skills, so which is like, let's say pick vegetable, cut vegetable, wash them, put them in plates, like, I don't know, stir. So it's only finite number of skills. But then let's say you have around 100 skills now, and then you can then combine them in various ways. So it would be like 100 CX, where X is the number of tasks that you want to draw in order to do a high level sequence. So something like make an omelet. So that's like, I don't know, open the fridge, take an egg, break an egg. Even with like a finite set of skills, you can still do a lot of tasks in the real world by combining them, and a lot of like high level instructions. We still have a lot of skills to go. I think with RT1, the objective was how do we get an algorithm that shows like scaling limits. So if you look at the scaling plots in there, task diversity is very important. RT1 doesn't seem to saturate with the amount of data you throw in. And in fact, it actually seems to like get much and much better with like emergence at like higher scales and higher diversity. And you can also increase the size of the model a lot to fit the data. If you imagine that you have to build like a very generic robot manipulator, you need data and you need a data absorber. So in our office, we call it like a sponge and a fire hose. So a sponge is like RT1 is a very good sponge. And we are also building like better sponges there, which is like, I don't know, like VLM, like foundation model transformers, right? Which can transfer also like internet scale generality into robot manipulation. So like visual language models as manipulated. Like, have you seen the Palmy paper? Something like that. So now imagine that you do have a data sponge that you can put a lot of data and then it just learns and then it does them in the real world. Now the question is, how do you build a fire hose to like really pump it with like a lot of data? So that's one of my main projects at Google. So like how to scale autonomous collect, also how to like mine for a lot of data from the internet.
Tell us more about that. I mean, I'm understanding from your commentary that it sounds like are kind of trying to base this on video of humans doing stuff, which this is always kind of an interesting pattern as well, where it's like a lot of times the hardest part is figuring out how to cast the problem in such a way that you actually have or can create or can sort of, massage existing data into form where it can actually, power the training paradigm that you want to power. So obviously there's a lot of data out there, whether it's NBA basketball games or, how to stuff of all kinds on YouTube. I guess a couple of questions that come to mind there. One is like, there's so many different possible forms of robots that, kind of if I was thinking about this naively, I would think, okay, maybe I need, does video work? Or maybe I need like a first person, like POV, GoPro type of view to make this work. Cause that might be a little bit more analogous. Boy, there's so many different possible forms of robot. Obviously you'd want this foundation model to like be able to adapt to all kinds of different form factors or embodiments, if you will. So I guess those are my two questions. Like in the sort of pre-training, do you think that like the third party point of view, like the NBA basketball camera from the side view is going to be enough to kind of develop the conceptual, semantic understanding that you need? Or is there going to be kind of a need for like more specialized point of view type thing or something else? And then second, is this kind of inevitably shaping up to be like a two-stage thing where there's sort of first like building the representations of what the humans are doing and then later like a bunch of adapters to specific, forms? What am I getting right and what am I getting wrong as I guess there what that might look like?
So some of the things you can actually transfer, right? Like let's say I see my mom cooking an omelet and then from third person view, and then I can try to cook an omelet and I'm mostly successful. But if I see Kobe Bryant playing basketball and then I try to play at that level, I'm not going to be successful, even though I have a very good modeling of my own body. So I think it's going to be similar like that. A lot of tasks, like whatever is easier, you can learn by like third person watching, but there still are tasks that you can only do by actually practicing and improving your own control model. We have some good work coming. Like I don't want to speak about it before it's published, on like transferring between human and robot data, and also training larger VLMs for control.
Just the one that came out this week, Palm E, was pretty amazing. Kind of inherent in that, the big project is the E stands for embodiment, right? So we're taking Google's kind of signature language model, which has been adapted to, seemingly every domain already. I go on and on about MedPalm in other conversations, but this is Palm E. So kind of sitting it at the center of this robot system and having it do the kind of reasoning and planning. Pretty amazing. Definitely picks up on another theme too that we've talked about a few times, which is the model to model communication. If I understand correctly, with Palm E, the kind of auxiliary models are trained to inject embeddings into the language latent space directly without going through language itself, right? So there's this kind of really interesting connectivity that's starting to happen across these models. That's something that we also talked to the blip authors about, and that's been a technique that they have used in their most recent paper as well. Translating these predictions to actual action in space and accomplishing stuff, that's very particular to robotics, obviously. Can you kind of talk us through that half of the equation?
I think the key to building like a foundation model would be data interoperability. And if you look at PAMI, it converts images into tokens, language into tokens, and actions into tokens. And once they are tokens, then like a transformer can like operate on all of them. And also, if you really think about it, the foundations of like thought is similar in whether you're acting in language space or vision space or action space. And to get a globally optimal solution, you need to think in all of these spaces, right? Like if you are a person who's cooking or cleaning or walking your dog or your kid, you are thinking in both in language, in vision, and also with like your body. So any solution that would be like a globally optimal solution will be fully multimodal, and I think eventually it would be like one model to rule them all, to like does all the modalities together. And specifically, the way I think one of our T1's innovation is tokenizing actions. And at any given point of time, at least for the EDR robot, we have like 11 variables for one to terminate the episode or not and decide between arm and base control, and like around 7 variables for arm control. And for arm, we are only doing basically where to put the end effector, so end effector positions, end effector rotation, and how much to close the gripper. So 3 variables for position, 3 variables for rotation, and 1 variable for gripper close. And then for base, X, Y, and the angle. So three variables for base, 7 variables for the arm, and 1 variable to decide to control base or arm, and then to also terminate the episode. So once you like make your actions like tokens, then it's just like vision tokens or language tokens, right? Like it's actually kind of like it's very radical. When VIT came out, people were like, oh, this is not going to work because like how can you convert an image into language as like a sequence of tokens? Language is a sequence of characters, but then it works, and it was able to bring us like large multimodal VLM models like Clip, even Stable Diffusion, DALI, and everything which is built on top of like Clip like models. So then the question becomes like, now can you also add actions in there like tokens? Like now actions look exactly like language, and it's just a question of predicting like 11 tokens after, and you can do that for any robot. And maybe another robot has like more degrees of freedom, like let's say imagine like a humanoid or something, and then you have a lot more variables. So each degree of freedom can be like one extra variable for the transformer model to predict. And then it just becomes like, can you predict the XYZ sequence? That's how I think actions are going to be tokenized and converted into data for transformers.
So at each step of inference, the kind of core language model, which is, you're kind of projecting out in the future, there might just be literally one big model that takes everything in and, it's one huge black box. But for now, we kind of have some auxiliary models that like do the vision part and kind of feed that into the language. And I looked at the Paul Me paper. There's even like a couple different types of language of vision model, that, object segmentation, general scene description, depth mapping, whatever, like all these kind of different things come in together into the language model, along with, of course, like, what are we trying to do here? What did the human ask us to do? And then what is spit out the other end is 11 values, which say, and was it either or? Like you're either going to do something with the arm or you're going to do something with the base?
So RT1 is like that, but our next models are going to be whole body control. So which means that you move both of them together. If you really think about how you do your control, you are not either moving your arm or your head separately, right? At any given point, you move them together. So yeah, that's going to be fixed.
So there's kind of a couple, I'm understanding like a couple of different paradigms here or ways that this could work. One would be that the language model says, like, okay, based on what I'm seeing and what I'm trying to accomplish, I want to move the base to position X and Y. Okay, cool, we got there. Now, next time, I want to move the gripper to position XYZ and, have a certain angle and have a certain, open close. How does the sort of issuing of that command relate to the cycle time? Because I would assume that, like, you can only accomplish so much before you're going to be kind of running the whole process again.
So that's like the action bound, right? The language model basically predicts a token, and the token is like a value between like 0 to 256, but each of those numbers correspond to like a certain bound between no action versus go forward or backward. The language model is predicting still within like a bounded space of action that you can go to or not. And in RT1, the inference time was 100 milliseconds, and then the full stack time was 300 milliseconds. So that's like 3 hertz control. Humans are a lot faster than that, and yeah, we know that we need to optimize it, but these are research robots, which is why the stack is slower. But production robots would be like a lot faster than that. And also, let's say, assume that once the language model says go to XYZ position or whatever, and we are doing concurrent or non-blocking control. So what that means is that um, after the language model tells the robot to go move to that position, the next cycle of inference does not wait until after that action is executed to start the next step of inference. So there is a thinking cycle which is going, and then there is an executing cycle which is going. I mean, this is also like how you do it, right? Like you don't wait until, let's say, I don't know, you grab something to think about what is the next thing to do. So thinking and acting are happening simultaneously, and it is also important uh, for robots to be fast, because like there are moving objects. Let's say if your kid throws you a ball, uh, you need to be dynamic, and if you are slow, if your control is too slow, if you move like that, then you're not going to catch the ball. So which means that it imposes certain limitations on the latency of the whole system. So one of the ways in which we tackle that is by using the token learner, which is like really compressing the tokens from the pre-trained efficient net, and so that the inference times are faster, and that cuts the inference time like 1/3. And also in language models, it's like everyone is excited about like really really big models, but scale comes with emergent properties, and scale comes with like large reasoning abilities, but then that also means makes inference slower. So they are sort of like competing objectives. So we want fast control, but we also want to fit as much information, as much context as possible. And definitely, like in the future, our hardware, our inference hardware, all of that is going to be much faster and optimized for transformer inference. But right now, there is still that competing objectives.
Okay, that's really helpful, and I think likely very clarifying for a lot of people. If I understand correctly, there too, like the command, I guess, right, the predicted command of go to XYZ, that's explicit enough, I gather, that it can be just sent directly to the robot control system for execution. But then with the latest paper with Paul Mee, it sounds like there's a bit of a different architecture where it's starting to, instead of saying like go directly to XYZ, it's giving like slightly higher level commands that are then received by and translated into actual action or motion by another model within the same system. So can you describe that version as well? And then maybe like the pros and cons, like why Is that just a strictly better approach, or do they have, trade-offs?
Yeah, so actually, PAMI and RT1 work together. So PAMI is like the updated SECAN, which is converting high-level language into low-level language. So converting between like how to go get coffee and then planning that with like feedback from the system and everything. And then RT1 is doing the little things like pick up the coffee cup. So I think two models are like optimizing both of them is synchronously is suboptimal compared to having one model do both planning, language generation, and inference control. And I think like that is the way that we will go in robotics. We are not. You'll see future papers from us which go in that direction. Yeah. So PAMI is more like SECAN level, like reasoning about the environment, but also it is also doing like affordance. It is also doing like scene feedback, and RT1 is doing the exact actions.
Palmy, the successor to Saycan, will take in everything that's going on, which includes my having told it to get a cup of coffee and its knowledge of its position and state and its, visual input. And then it will translate that to a low level command that is like, grab the cup. And then RT1 takes that input in and translates that to XYZ coordinates for the gripper. What does sound nice about that architecture is you could have like RT2, 3, 4, 5, and 6 for different kinds of robots. But does RT1, it already handles multiple different types of robots as well, right? So is that just like a variable within the bigger thing? Like what kind of robot arm you're actually controlling? Is that just another token that's in the input? Or how does it kind of know which embodiment it is controlling at any given time?
So it has another input. So when RT1 was jointly trained with KUKA and with EDR, it was told where like the data came from, and the action spaces were also sort of mapped together. Yeah, so one way that you could compose like a one model on like multiple robots is like using one token to determine like which robot you're inferencing on. So let's say imagine like if you're running like a robot dog and then you have one token saying this is a robot dog, which means you predict like I don't know, maybe 24 variables, versus if it's like the everyday robot that we are doing, then just predict 11 tokens. That's one way where you can like still mix a lot of different data from a lot of different robots and then also have like transfer between them, while allowing it to inference on a lot of different robots.
One of the videos that I thought was most striking from was an example of where there's these sort of exogenous shocks to the robot's plan. For example, there's one video where the robot is picking up a bag of chips out of a drawer, and then the human comes in and knocks the bag out of its hand and puts it back in the drawer. And so it's a demonstration of the fact that the language model, especially as it's informed by the visual inputs, loop, obviously it's not having these conscious thoughts of like, oh, somebody knocked this thing out of my hand, but it is realizing the bag is over there and, I need to go back and get it to pick up my, to accomplish my objective. That's a pretty striking video. There's one with pizza being made as well and sauce being, kind of smoothed around on the pizza, and the person comes and moves the pizza, and the robot recognizes that and continues to apply the pizza sauce appropriately. So I was like, boy, that's pretty awesome. And then I was also thinking, what is the limit of how much perturbation I would want a robot to sort of push through in the real world? And I have a 4-year-old kid and a 2-year-old kid and another new baby coming in, let's see, 25 days. It's definitely a very common occurrence in our house that I'm trying to do something, and then there's a shock of a kid entering the scene and messing something up or whatever. How are you guys thinking about sort of okay, this is sufficiently big of a shock, that we did not that the model did not expect, that maybe it's time to just stop. Like I should not pursue this goal anymore because something is happening that like, is out of distribution. I don't know what to do with it again.
So these are like ethics questions, right? So it's like not a question of can you do it, but should you do it? And it's also like very similar to like safety questions. And here, our straightforward approach is to borrow from like AI safety, AI alignment research. So one way, like we are running a lot of autonomous scale operation. So like where the robots run around and then they propose what tasks to plan to practice, and then autonomous policies then try to attempt to practice those tasks. But now the question becomes like, imagine the robot is roaming around people's desks. It should not attempt to pick up their personal belongings. Or if people are sitting in the Google micro kitchen, it should not come near them and then like try to disturb them or like propose any task that is harmful for them. So like for example, one of the days there was the robot that we were planning, and it detected that there was a phone in my hand because I was recording it, and it was like um, uh, take the phone and then pick up and then put it on the table. But the phone was sitting in my hand as a human, and I would not appreciate it if it just like grabbed the phone from my hand without any consideration for like how humans behave, right? Like before you take my phone from my hand, firstly, you need to understand that the social norm is to not grab people's phones from their hands. Secondly, you would ask for these things. So there's a lot of like HRI components in there, which is like how can robots be like nice and polite even in social interactions. And we have a group that is working on HRI research, which is like thinking about like um, how to make the robots polite, how to make them reason contextually about these things. Like for example, in this failure mode, the robot detected a phone in the scene and proposed a task, but it did not detect that the relational aspect of the phone being in my hand and the fact that I was holding it. If we have better scene description, I think a language model would be able to reason that this phone is in the hand of a person. So then, don't do that. Um, and so currently our approach to safety now is asking a language model, like, should you do this or not? We also have like for tasks like collision and stuff, we have like more harder bounds, like it would not do tasks that actually have collisions. Even if the language model plans and everything, it is still like bounded. It should not be like dropping objects or like colliding into things. So there is a hard bounding from a control perspective, which is just like don't run into anything. Then there is the question of like asking a language model, is this a safe task to do? Is this a nice task to do? Or if not, can you explain to me why this is something that you should not attempt to do? So some of the tasks is like our robots right now have only one hand. So when it is given a task that requires two hands, then it should be like, I'm not able to do it because I don't have two hands. Or if it's asked to lift a heavy object that's above its payload, it will be like, this is unsafe for me to do because it's a heavy object. Or if you say like pick up the thing with the hot coffee, it'll be like, this is a very hot object that I should not be handling. So maybe you do it. So like, so, and then, so now here we come into the realm of collaboration between a human and a robot, where the robot is closing the loop in itself. Robot knows what it should do, what it shouldn't do, what it can do, what it can't do, and also how to be nice while doing these things. And now, so once it can classify these things, now the question is like, you should still be able to get the coffee to the human, even if it's hot coffee. But if you are not able to handle that, if you think you're not safe enough to handle that, then you need to replan and reason about how to still get that task done. So one way could be you can like chat with the robot. Our robots have like a chat interface. You can tell the robot back, hey, the human back, hey, look, the I have the hot coffee in there. Can you come help me pick it up? Or so that is the realm of like collaboration and or like intervention. Like so. I think deploying robotics in the wild is not going to be with fully autonomous policies, but with autonomous plus interventions. So, like how self-driving cars are, right? They are good for handling. Autonomy can handle like 95, even 98% of cases. But those like those 2% of cases were like, or even 1%, if you run at like 10 hertz inference and you have 1% mistakes, you are making a mistake every 10 seconds. And that's like highly unsafe. So, but what the self-driving cars are good at are knowing where they're good at and where they are bad at. And they can ask a human for help when, let's say, the map is doesn't make sense, or like there's a person there saying, asking the cars to go around. So similarly, I think that the way that robots will be deployed is like they know their bounds of operation, and they also can ask a person for help when they are confused or when they can't do something. And they also have like hard bounds around them, like common sense things, right? Like don't hit a child, or like don't run into things. And even if a language model somehow plans like hit a child or whatever, then you still have like safety on robot, like control, which is not a machine learning model, which is deterministic control that says like don't run into objects.
That sounds like, for one thing, kind of another Herculean labor to collect all that data, because that's another level that doesn't really exist, right? Or maybe you're in the process of collecting it now, but there's not really a lot of examples, certainly out there on YouTube or whatever, of robots running into situations where they, determine that like they can't do the task.
So definitely, I think that we will get a lot of transfer from a language model, like all the work that people are doing for alignment and safety of language models and other, now with like GPT-4 or multimodal models, like don't generate harmful output, don't ask it to do harmful things. So that's definitely going to feed directly into our research that's there. But we also need more information about the specific failure modes of our data, of our problem. And once it is close to productization, so like how Waymo or like self-driving companies have their simulators to test for safety related things, they also have like human in the loop, which is like constantly testing the hardware. So I think all of those things will come in. But robotics especially has like a particular imposition on safety, which is that language models can be wrong on the internet, right? You ask chat gpt something, it goes wrong, no problem, or it says something weird, no problem. But then if you make a bad plan, if you like drop an object, you break things, you cost money, and you probably injure a person or destroy an object, which is so there is a higher penalty of a failure on robotics models, which is going to be very important towards their safe deployment. I don't think that this is an impossible problem to solve. Look at self-driving cars; they're already making money in San Francisco. So it's just a question of us doing it carefully with human in the loop, and then rolling it out in phases. Yeah, initially everyone was like self-driving cars would never work because they can never solve 100% of the problems. They're always going to be long tail and whatever. But yeah, you don't have to solve the long tail. You can solve as much as you can, and then you can make humans solve the rest. So you're basically doing intervention. Assume that the robot already works, like start making money today and then keep solving the problem, then reduce the intervention rate. So then that becomes your whole problem. I think bringing robots to people's houses will also be like deploy today with whatever like capability you have, and then use humans to fill the gap of your algorithms right now. And then as you go, as you make money, as you keep improving, slowly phase it out.
It's funny you mentioned the self-driving cars too. I just took a ride in my neighbor's Tesla that has the full self-driving enabled, and I came away from that feeling like, first of all, just pure wow. Like it really does work amazingly well. And also like nobody seems to be acknowledging it. It's this odd, as you said, like people say it's never going to work. Like you can still go online today and find, recent articles. Probably can find one from today that says like FSD is never going to work. But I just wrote in one, and it definitely is a lot farther along than some of the, the naysayers would suggest. So it sounds like robotics from this conversation is probably in a similar position. I wanted to talk a little bit more about kind of the hard bounds, because that also is something that seems, as you just kind of spoke about, much more important in the robotics paradigm than language models or others. One article, just for listeners, that I really recommend, because I could go back to it repeatedly just to kind of meditate on like how I work as a human, is this Scott Alexander book review of a book called Surfing Uncertainty. We could put the link in the show notes, but basically he kind of talks about how the human like biological nervous system just has like a ton of layers, and you've got like the prefrontal cortex layers are kind of the highest layers that deal with the highest level of abstraction, and then obviously radically oversimplifying, but as you kind of go down the nervous system all the way out to the periphery, there's just like layer after layer. These are probably not discrete layers, but to some extent there are discrete cells, so there is some amount of discreteness to it. Anyway, whatever. It's not meant to be too literal, but as you get out to kind of the periphery, you have just like very low level interpretation of what's happening, and you can do things like remove your hand from a hot stove before there's certainly any conscious thought of the hot stove. So all of that, and I highly recommend that article. All of that to just kind of preface like it seems like robots need something similar, right? Where they need to sort of detect that like I'm encountering resistance, or like the thing that I'm grabbing is like deforming in my grasp more than I, expected it to, or more than it seems like it should. And therefore I need to kind of back off, right? I need to like slow down. I need to, I don't necessarily want to wait for the next inference cycle to withdraw pressure or, back off of a collision or whatever. So how is that working today? Is that like is that more of like a classical system that's not AI driven, or is that also, something that the models are ultimately going to handle in your view? Like what's the future of that look like?
So let's go back to the example of the touching the hard object, right? So there is like the planning in our body, which like goes to the brain and the spinal cord and whatever, and then tells you that you should not touch the hard object. But then when you touch a hard object and then you reflectively act, you are not going all the way to run the inference step. This is what I was previously talking about by various layers of safety. There is one layer, which is the language model telling you, should you do it or not? Don't touch hard objects, don't handle whatever. But there is also like low level control layer. RT1 also has its own like safety. It will not do like highly unsafe things because it doesn't have the data, and it is like the data is cleaned and everything. But also on the robot, on the control level, just with like the C++ code, there is also a way to determine like don't do collision related stuff, like don't run into objects. And that's very easy to detect, right? Like the occupancy in space, don't deform the object, like don't run into things. But also more than just collision, there's various other types of feedback, right? Which is like tactile sensing, which is like as you said, right? Like if you try to pick up like a full bottle and I don't know, like if it deforms a lot, then maybe don't do it. Or if it's like if it spills over, don't do it. So right now our robots don't have tactile feedback on them. So like with the gripper, so it knows some, like it has some pressure feedback. So if it's like a very hard object and then you squeeze it, you won't be able to squeeze it, and that's reflected in the like the max torque applied onto the thing. But then there's also like more softer feedback, like to like cut like vegetables or like soft objects like tomatoes and stuff, you need more finer feedback, which is not there yet. But then we can still do a lot. We can still deconstruct safety into various layers with existing like just force feedback.
So I think that's reassuring that there's like that it's not fully a black box, that there is this kind of C++ safety layer that is like a hard override. And zooming out just a little bit more still, and just kind of like returning to some of our very early discussion around how we'll interact with robots, what kind of role they are going to play. How fast do you ultimately think we will want robots to be? As I watch the videos, it is notable that they run pretty slow today, certainly like much slower than humans. Like the videos are typically shown at like either 4x speed or 10x speed. I've seen both. So they're pretty slow in today's world. Obviously, you'll want to speed them up. But I wonder if you have like a sense for what the optimal frequency is for a robot to be operating at in a human environment. There might be a maximum at a certain like human-like frequency that would be sort of accessible. If we could run them at 1,000 hertz, I'm not sure that we would even really want to.
Frequency of inference is not the only variable for speed. So think of frequency as how reactive you are. So even if you're running inference a lot, but each step you can only move a little bit, then let's say to go to here, you're gonna, let's say, run like 10 inferences, but then you can also go to here in one inference, right? So there are two variables to control here. One is how reactive you are and your inference frequency. But second is also like how much movement you are allowed in each inference step. Time to complete a task is within 2x or 3x of what a human would take for that task. And then that is about optimizing both the machine learning on robot software and also optimizing for both reactiveness as well as speed. We didn't play around with speed a lot because it can be a little bit dangerous, right? You're trusting the inference a lot, but I think because these are research robots, we haven't really optimized all of these things a lot. When they come into production, then that becomes a more important question. But I think it's fairly solvable still with existing machine learning models and existing robots to get at least like within 2x of a human. Robots, you would be freaked out if a robot were as fast as you in doing things, right? And as good as you. I think it's fine to give them a little bit more time until they like, I don't know, ease into society and people are like okay with them.
Yeah, totally. I agree with that for sure. I have the most advanced robot in my home right now is the Roomba, and it's kind of stumbles its way and crawls its way around the house. It's not too smart and doesn't figure things out too quickly, but it kind of feels appropriate, and like we run it overnight. So it's one of these things too, where it's like, it doesn't really matter if it takes it an hour or 2 hours or, whatever, 5 minutes. Like it wouldn't be much better for me if it was a 5-minute task, for the robot instead of an hour. But honestly, probably wouldn't be any better for me. So yeah, I do think you're right. But it is also interesting to hear that perspective that increasing the frequency of inference really just smooths the behavior as opposed to really changing the behavior. And then you have a separate decision to make around like, okay, per unit time, whatever that interval is, how much am I going to move in that unit time? So that's something you can kind of control independently, that's helpful because I hadn't really conceived of it in that way. What are they like to work with? Like, do they break a lot? Do they need maintenance? Are they heavy? Like how robust are these robots that you are currently working with?
So I've worked with space robots. When we were in grad school, we sent a little robot to the moon. I have worked with like self-driving cars, and I have worked with everyday robots. And I think these are the most stable, at least at the fleet scale they have. And they are fairly robust. Like the navigation stack and everything is fairly reliable. They don't break as much. They don't run into objects. Like everything works. And I think it's because like Google's really good at engineering, and we also have like great ops folks who are like keeping everything like it's like oiling the machine, right? Like, and they are fairly robust and fairly good robots so far. I think they don't break easily, and it's very convenient to like run experiments on them. We still have a long way to go with like solving smaller issues and stuff, but I think they are the best robots that I have worked with so far. And another thing is that like you see industrial robots, right? They are also fairly robust, but they are very constrained environment. Like it's like fixed base, it's like doing picking or like it's like doing scanning. But these robots also move around. So compared to the complexity of the domain that they operate, I think their reliability is really good.
Do you think that they are the right form factor for like ultimately, use in homes?
I think form factor is a very, very important question. And there's a lot of like debate among roboticists on like what is the ideal form factor. Initially, a lot of robotics was like fixed base. So they were just like these KUKA arms and stuff. They would just like do things from a fixed location. But this is not very general robotics, which is why we now have like arms moving around. But the arm is the most costliest part of these robots. So if they have like two arms, then the robots is going to be almost twice as expensive, and then the equation, the economic equation, would not work out. So there are like various ways. So cost is one trade-off. Up until this point, we were limited by the robot software. And so if you cannot even do one hand task, then it doesn't justify having multiple hands and legs and whatnot on the robot, right? But now we are seeing that we are limited. The robot capabilities have increased to a point where we are actually limited by the hardware. So we have cracked a paradigm where it's like throw data and then just learn it. So then the question is like, how much data can you throw, and then on which robot should you throw the most data? And I think that if you really think about it, if you really think about like the ideal generalization, like a superhuman physical intelligence, it's probably going to look like humanoids, right? Because our world is designed for humans. Like your kitchen is designed for humans. A car is designed for a 6 feet human. And a cup is the dimensions of this, like what fits in my hand. A lot of the data on YouTube is from like a human egocentric perspective, with like human hands operating. So if you look at it from a design of the world perspective, then humanoids are the most optimal form factor. If you look at it from a data perspective, like NBA basketball agents playing, they look like humans. So then, and you probably need like a human-like form to play very good basketballs, right? Both from a data and a utility perspective, humanoids, I think, are the ultimate form factor for robotics. But if you really think about it, stability is a very very hard problem to solve. And Boston Dynamics has like really complex robots, which all of them are leg robots. But stability is a very hard problem to solve, and then that means that all of your problems become stability problems. While you're like picking things up, you are also worried about like falling. And if you do fall, you are at danger of breaking parts or injuring other people. So I think that one of the reasons that Boston Dynamics has like little stubs for their arms is because like they invested into legs too soon, and then now all their problems are stability problems. So initially it was one arm on fixed base robots, then one arm on mobile based robots, and we like now we have navigation and manipulation together. I think the next is like bimanual manipulation. A humanoid on wheels is basically two arms and a camera at human height, right? It's not like, it sounds so complex, but it's actually just two arms and a camera on wheels. So I think that would be the form factor for a lot of like indoor and office applications. Like most homes nowadays have like, most offices have like elevators and stuff. And for most robots, like if they're on the floor, they can do a lot of things. And then the next step would be like leg robots, which adds an additional level of complexity, right? Because imagine that you do build a superhuman intelligence and then it goes to deliver, but then it can't cross a little curb in front of your door. So you need legs to like go upstairs or go past curbs, or even to do like outdoor robotics. So humanoid on wheels would be the next version with two arms. Then would be like legs, and also or like fingers, like 5 fingers. Would be another upgrade, because a lot of things you can do with just grippers, but then fingers are highly complex. Like we have so many degrees of freedom in here, and it's highly complex to plan and stuff. But ultimately, a lot of the tasks would need more finer, dexterous manipulation.
As you're describing that, I have this kind of image in my mind that's like analogous to the human evolution, where it starts with like the great ape or whatever, and then it gradually sort of becomes more, to human over like 6 steps. You basically just described the 6 steps that goes from one arm to, the ambulatory robot. It's a pretty similar, evolution, so to speak.
That's why I'm so excited about robotics, because it's like we are inventing ourselves, right? It is in many ways a quest to understand us and our intelligence. And it's so hard to put down onto paper how we detect like a cup, or how we are doing these things, or how we are planning tasks. Like at least high level things you can like describe in language, but low level manipulation, low level inferences, you really cannot. Like why your arm and leg are moving in a certain way, you cannot. But then building, like, how software engineers say the best way to learn something is to build it. And I think robotics is basically our quest to understand ourselves and build more of ourselves. if you think about GPT and language models are doing a lot with respect to like scaling intelligence, right? And bringing down the cost of knowledge work. Like if you think about it, industrial revolution has automated a lot of mechanical labor that our lives are much easier. And now with the intelligence revolution, we are like automating a lot of knowledge work. But then truck drivers in the United States make like 200K because no one wants to drive trucks. Even like people that like sand boards apparently in San Francisco makes like $95 an hour, and which is like comparable to a software engineer. So as the availability of labor changes, once like more knowledge work gets automated, physical work is going to be the most valuable. Like when my friends ask me like, oh, software engineers are getting automated, artists are getting automated, it's like the Moravec's paradox, right? We thought the things that we thought were hard to do are actually easy to do for computers, but the things that we find are easy to do are really hard. Like we for us, like composing these images and stable diffusion is like super hard, and editing those things. But then computers apparently can do that. But something so easy as like going to my kitchen and make me a coffee, or like take my dog for a walk, that we take for granted and we think is so easy, is like really, really hard for computers to do. So, but physical labor still accounts for a large portion of our GDP, and automating that has like a lot of economic opportunity. And I think eventually, if we think of like our species like really going forward and capturing different planets or expanding ourselves, then definitely solving both AGI in the digital world and AGI in the physical world is going to be very important.
We had Suhail from Playground, which is an image creation service that people are obsessed with. He has a young child as well. He said, maybe my kid, who knows, like maybe some of their best friends will be AIs. And then we also had Eugenia Koida from Replica, which is the like, virtual friend app that, is all digital today, which people are already falling in love with. And that's become like a big challenge for her because people are doing like, erotic role play in the app. And she's like, that I might have problems there in any number of ways. So they just kind of dialed that back, and they had a bit of a backlash from users because people really care about that stuff as they become attached to it. Is there anything that's like blocking in your mind the sort of extension of, when I think of this, I just think of like picking up the toys. Like that's where as far as it goes typically in my imagination. But then, when I think of Suhail and his kid, and I think of Eugenia and all her users, it's like, boy, are we going to have robots that are like playmates to our kids? Are we going to have robots that are like robot spouses?
We are gonna have them in our lab, like on days like I'm like driving to work, and then I have booked like two robots to like play with me the whole day. And then at the end of the day, and you get close to these robots, right? Like you are like, this Meta or this one, they have the numbers at their end. And then you're also like, at the end of the day, I like cracked one robot's wrist because like I moved the chair against it. And then you spend the whole day with it, and then you're like, okay, I had to like file a bug to take it to like it's like a hospital kind of service that they have where they fix the arm. But like I felt like so bad that I broke the robot, but the robot would never understand that I'm actually sorry. And I would not even, the robot never told me that it's okay. But a human, if I would hurt a human by accident, they would tell me that I'm gonna be, it's good, it's okay, and I would feel better about it. So that's one thing. You eventually start anthropomorphizing these robots, right? Because now they're also getting smarter with language. Like I can tell it, let's go on a walk, and then that language command is enough for me to like take it on a walk. Or like it, I can like teach it things, I can talk to it, or it says like sorry for doing something. Or I think sometime we had like a little bit of like creepy programming on it, where like you're working in the kitchen, and then it would like go up to you and be like, hey, are you my creator? And I'm like, dude, what? I already feel I already feel so like, when I wrote my bio as mother of robots, it's because one day I was like sitting in our robot classroom, and I'm like, oh, is the robot better at doing these things, or my dog more consistent at like instruction following? And I'm like, oh, maybe we should like have a face off between them. And then I'm like, wait, but whoever fails, I'm going to feel so sad because both of them are like my babies. And I'm like training both of them. And that's when I'm like, they are actually an extension of us, right? If you think about language models, they are basically condensing all of human history, all of our experiences. And with multimodal models, like all the videos that we are collecting, all of our information about the world, all of our even like more private thoughts, all of our fears and everything. So in some sense, they are a distillation of the human mind itself, and not just one human mind, but a human mind across history, and a human mind that is sort of also omnipresent in space and time. And in when you put it on robots, it's like a human mind distilled, but also with physical capabilities. I can see that becoming really, really close to like being um, being human, and maybe in the future, right? Once we have BCIs or whatever, like I really believe that like the future of machines is also the future of us. Imagine that 1000 years later, our bodies have exactly the same skills as we have today. That would be so disappointing. But I imagine that, but I think it's very possible, like with Neuralink and everything, we have BCIs, we have more powerful compute on us. Like eventually, like we merge with machines in a way that they are like our progeny, which is also one reason why, like, I'm not that worried about like AI taking over the world and how they like if and this might sound a little bit defeatist or controversial, but if they are in fact smarter than us, then I would want to be like merged with them and have a common future with them than to be like it would be like if monkeys said that humans should not be formed, right? If they are actually superhuman and so much better, then we should just become one with them.
Love it. Fascinating. I assume that inference is going to kind of have to live on the edge for practical robot deployment. It seems like the latency of like going back and forth to the cloud is probably not viable if you want to run at like 10 hertz or whatever. So first of all, like, is that right? And then second, what about sort of on the edge fine tuning? Is there a paradigm that you see in the future where, these robots will learn, the layout of my home, to take like one very simple thing, or like our preferences, and start to have kind of a more customized, like, the sort of final finishing training would be like done in deployment, by kind of human feedback, but like from the customer, the actual, homeowner or business owner or whatever the case may be. How do you think that shapes up long term?
So I used to believe that you needed to do onboard inference for robots, but now we are seeing with like larger models like Kami and Pali that we are running on the robots, we are actually doing inference on a different server and then pinging back and forth. And so far, the latency is still good enough to like go do that, and then I think it would be very hard to run like bigger models on robot. But then this is still new technology, so we will have to see how they evolve. So maybe in the future we have chips that can run like multi-billion models on robot on device. That would be great. Or we have some way of like fixing the latency so that like it is at least right now it is still within operational limits, it's still good enough. With language models now you are seeing like more personalized AI, right, where you can shape the character of AI to like even with prompt engineering or even with like fine tuning on top of like an existing language model. You can customize it to your application. Like it has like various different advantages. One is like privacy, which is that you don't want to give your data to some large company to put it in their training set, but you want to keep it in your house or in your office, and then a little bit of fine tuning on top to personalize it. Or even like, yeah. So I definitely think this will also be the way that once we build like a foundation model for robotics, I think we these paradigms will start to happen. I definitely think it has to be it has to be fine tuned, right? Like imagine a robot that is in your house. It has to learn the preferences of you, your kids, your schedules, how you like certain tasks to be done.
I noticed that there's, I believe, more than 50 authors on the RT1 paper, and you've given us like a little bit of a couple different angles on like, oh, a hospital service for the robots. I'd never thought of that. Can you just kind of describe the team that has to come together to make all of this work?
Firstly, I want to say that I have an incredible team at Google. They are like, one thing I'm realizing in life is that to do great things, you need to stand on the shoulders of giants and also work with like really smart people. And my colleagues at Google they are like the smartest in the world. They are the best in the world at what they do. And they are still so humble and so curious. And you can challenge them, you can ask them questions. And it's like really nice to show up to work and be heard for your ideas and be respected and to work with like world class people. And now the way that we organize these large efforts, so we have like the big papers that we do, and we also have like splinter papers. Splinter papers are usually like smaller collaborations, like intern projects and other things, and big papers are like more foundational, like like upgrades in robotics technology that we publish as an entire group. And the way that this works is like someone leads the effort where they are. But then everyone's included because we like doing robotics takes a lot of people, right? Like everyone who's in part of the ops and keeping the robots running, who's collecting the data for it, people who advise, people who actually implement things and like train and evaluation. The bigger papers are fairly inclusive, and then we try to like bring everyone on board to publish like the large upgrades in robotics technology. And for the smaller ones, it's usually like people involved, and then they have different guidelines and stuff. And at Google, we always lean towards being inclusive and sort of including as many people as we can.
The role of AI in your personal life right now, are you using any particular products, services that you find exciting and would recommend to people?
So I use Bard or even ChatGPT sometimes to like ask it questions to do like one of the things to explain code whenever I'm writing new code, and like especially with web programming and stuff, you are writing a lot of templated stuff. Just asking Bard and ChatGPT is like very useful for like tail queries and that like search engines are not that good at doing. That's one AI product. Yeah, I also like the summarization thing. So these days in meetings, we are like, if we have a large meeting that's like running over time, you just like take the whole thing, summarize it, and then have these bullet points. But mostly I use AI to like code and even like make like fun poems and stuff. And nowadays, like whenever people ask me to like write emails, I feel so lazy because a lot of like being obligatorily nice in an email is just like filling it with text that you can just ask GPT to write it, right? So sometimes like when I get a lot of emails where I want to give like a short response, but then it would be impolite to be like curt, I would just put it in there and then ask it to make like a bigger email and then just paste it in there.
Secret safe with us. So let's imagine that 1 million people already have a Neuralink. And if you get one, it will allow you to type or create text as quickly as you can think. In other words, you have thought to text. Would you be interested in getting one?
Absolutely. Yeah. Why would I be not?
Well, people are a little squeamish about holes in the skull. So that's one common objection that we've heard.
But 1 million people have it, right? So it worked for them. In fact, I don't think that I would wait. I'm an early adopter. I don't think I would wait for 1 million people to get it before I get it myself.
I think I'm with you, and that's part of why I asked the question. But this has been actually one of our more polarizing questions. I've had a couple responses just like yours. I'm like, I didn't even need to wait for 1 million, and I've had others that are like, the last thing I'm going to stand for is something that can read my thoughts, being physically implanted into my body. And I do kind of get that. Although personally, I think I'm enough of an enthusiast that I would probably be with you on the earlier wave.
I'm also big on like privacy. So like don't do any private company products that like scan my retina or anything. But so if it's like running inference on chip on my brain, that's fine. But like if it's like sending my thoughts to a cloud to run inference, then I would not be okay with that. So yeah, there are like I think some constraints on like the bounds of how the technology works. I don't know. Yeah, I'm very curious and very excited also about it.
What would you say are your biggest hopes for and also fears about the places that AI may take us?
So firstly, I think AGI has a lot of promise in like both automating knowledge work, bringing a lot of utility into our world. Like I think in many tasks, in many of our so imagine that humanity is like pushing forward, right? Like we are making inventions in science, we are making inventions in robotics technology, a lot of these things, but we are bottlenecked on intelligence on many of these fronts. But imagine that there is like an AI scientist that can like propose hypotheses, run experiments, write papers. They can invent new things. Our world and our technology would like move so much faster. My hope for at least AI in this decade is hopefully we can train like an AI scientist, at least on a few things, and we can automate a lot of different types of knowledge work. Like software engineers could be much faster, doctors could be much better, and we are not then resource constrained on intelligence in our world. That would be amazing. And even in physical intelligence. Um, but of course, AI is a very foundational technology, very impactful, and it comes with a bunch of we need to do it correctly. One thing that I'm worried about is increasing inequality. Like if AI is built by large companies and then it like you use less and less labor, it leads to a certain level of centralization. Even now with like language models and stuff, there are very few people who can train like models that are like billions of parameters, and that increases the existing inequality already, and like a lot of people are left behind. I'm very concerned about that, and I think that the open source movement is going to probably try and equalize the field. So I'm really cheering on like Stability AI and other companies for leading that effort. Hugging Face also. The second thing that I'm worried about is AI safety. So I'm fairly an accelerationist. I'm for we need to build this, and we need to build this fast but also safely. But there is a finite probability that things could go wrong, and so we need to be careful about we also need to make sure that we solve alignment to a reasonable extent, that as we like phase out this technology into products, we are careful about how they are being used. In fact, I think that productization of AI is going to accelerate not just capabilities research, but also safety research, because ultimately only an aligned AI is a useful product. If it's not doing what people want it to do, but it's like gaslighting you to leave your wife or like threatening you, it's not a good product, right? So I think it's great that like Sydney Bing went first and then told people what a bad chatbot could be, because that gives the opportunity, that made everyone think about how important it is to build a really good chatbot, and it presents an opportunity to do this right. And I'm very excited for Google to take on that challenge and fulfill and meet people's expectations. I think we are approaching the development of AI in also a responsible fashion. We want to do this well, in addition to being one of the first in the markets. Yeah, so I think safety is one concern, and I think productization and acceleration of AI into products will also accelerate safety research. The third thing I'm worried about is bias in AI. So in addition to existential risk type of safety, it's also like I'm a person of color, I'm bisexual, I'm a female, so I'm a minority in various ways, and I know that like language models and other things have like biases with these models. For example, if you say go to Keerthana, it would not understand, but if you say go to David, it will go to because it's like because like Western names or male names are more represented in the data set. So yeah, so I'm concerned about like AI ethics and AI bias. I think it's important problem to solve in order to like bring the benefits of AI to everyone, and not just like a dominant majority of population. And AI is making everything data driven, and data is highly like it's like a mismatch. We have different distributions for different distribution of people.
Keerthana Gopalakrishnan, thank you for being part of the cognitive revolution.
Thank you for inviting me. I had a lot of fun talking about these topics, and great questions as well. I'm really looking forward to it. Was a very technical podcast, more so than any podcast that I've seen. So thank you for that, and I hope that your audience will enjoy.
Thank you, and I am sure that they will.
OmniKey uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in OmniKey so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.